they're very good, but the implementation is really limited. So I know about one Fortran code that implements that. So basically the idea is that you write so this is for the symmetric positive definite case, you write the Cholesky factorization, and then you write the matrix as a sparse plus certain correction, and you use this approximation. And then you can, this is a low rank perturbation, and yeah. So that's sort of factorization. Seems to work better, but again, people didn't bother much in implementing this in software that is typically used for research or for well, there are some in-house implementations, but yeah. So, and finally, quite fast, but okay. So, what else? Suppose we have a sparse linear system. Is there a Swiss Army knife that will solve it without any additional problems? So one Swiss Army knife would be incomplete loop, but even for simple problems, it doesn't give optimal complexity. So if the graph of the matrix is two-dimensional, it's not a big deal, because even a fast direct solver will work fine. But if you have, for example, a three-dimensional complex graph, fast direct solver just will not work, even for the size of the problem of hundreds of thousands, which is small by nowadays standard for sparse matrices. Incomplete loop probably will reduce the number of iterations and probably will give you a reasonable running time. But the thing that is most close to the Swiss Army knife is so-called algebraic multigrid. Algebraic multigrid method, it's a nice idea proposed by two Germans in 1987, Ruge and Student. Ruge died recently at the age of, I think, 70 something, skiing. He was doing mountain skiing, fell and died. So it is a good death or not, I don't know, but he was quite active. Bad things happen. Any case, it's not important to the topic of the lecture. So, well, if I'm going to sell you some methods, it's very easy to sell because algebraic multigrid is the only asymptotically optimal method that is black box. So you know there is a class of problem for which it gives you linear complexity given only the sparsity pattern of the matrix. And, well, at least for some problems. The memory footprint is also small, so it has hyperparameters, and in fact, again, if you try to apply it, for example, to two-dimensional problems, by two-dimensional problems, I mean problems which have like two-dimensional graph with like connections to nearest neighbors, then the running time can be large. So it's asymptotically optimal, but the constant is not small. So there is a code called PyIMG in Python, which works, but this is more like an academic, not a production-ready implementation. So the real production variants of algebraic multigrid solver are available in large C++ Fortran packages like Triinas, Hyper, and so on, which work. But again, using this software for research purposes, even storing this software, it can be quite painful. Yeah, but again, the methodology is large, and the history is that it is motivated by the idea of so-called geometric multigrid. So what you said is, what about initial approximation? And if you just given a matrix, it's not so clear where to get this initial approximation. But in some applications, it's very clear where we can at least look for the initial approximation. So suppose we have an equation. Okay, this thing just dropped off. Just went away. Trying to bring it back to life. so clear why it should be done like every. Well, the simplest example, suppose we are trying to solve this equation, and we can construct discretization with 4 grid points, okay, more grid points and so on. So we can basically introduce this, there is a continuous problem, and for each continuous problem we can introduce different discrete versions which approximate the same continuous problem. So you have the original problem, which is in fact has infinite number of unknowns, it's just continuous function, but it has a whole set of finite dimensional approximation. You may say that our original system is just the finest grid. Yeah.
It's very nice that you put equation here, but also it has what H parameters, because you need to put something on H, and also with the
Oh, H is just the grid size between 2 points. It will so
we have a grid, we can have grids and
yeah, we introduce the grid, and H is what is called mesh size. H is here, and it's H over to here, and so on. That's a typical way. That's a motivation. So in the general form, you have a matrix A, fine, and then, so remember, for example, the Gauss-Seidel method. In the Gauss-Seidel method, we fix all the components, but update only one. So it means we are looking the solution for the solution in a certain subspace. But another way of writing that we can create out of this matrix different smaller matrices which correspond to the projection of the solution on the Corsi subspace. So for example, we can take our matrix and consider every even element or every odd element and so on. So in fact, this idea of grids can be recast into the graph. So you need to do what is called graph coarsening. You have a graph with a lot of connections, then you union certain vertices of the graph into bigger vertices, and you can get a coarsened graph. And then you also need to define how you interpolate your solution from the small vertices to the coarse vertices, but suppose you just do averaging, weighted averaging. And then you can create a hierarchy of graphs, hierarchy of linear systems, in such a way that the solution of this coarser matrix linear system approximates the solution of a finite. So have this hierarchy. And you can construct it. So this is the first step. Construct graph hierarchy and smaller matrices. So that's the first step of the algebraic multigrid. So we have original matrix, which corresponds to the original graph. We coarsen the graph. So the next graph is basically obtained by merging the nearest neighbors' vertices. And then you construct the way. So every implementation of the algebraic multigrid has its own way of graph coarsening, has its own way of constructing these reduced matrices. And there is also a sequence of operators that takes the vector that corresponds to the slash space and projects, so it's called restriction operator. F, S1, L1, x2, and so on. And there is also another way that brings the operator back. So this is a sort of restriction, and an opposite way, this is sort of interpolation. You want to interpolate the solution in the points that you have never seen. Of course, there is an error. So that's the general scheme of the IMG algebraic multigrid hierarchy. Okay, how we can use it? Suppose we have constructed this hierarchy. How we can use this hierarchy to compute the solution? One way would be simple. Take the linear system, project the right-hand side onto a coarse space. Okay, suppose we only have just two graphs. One graph, another graph. This will be fine graph, this will be coarse graph. We will have one operator that does restriction, one operator that does prolongation. We have our original matrix A. We can write RAP, right? So the coarse matrix like this. This is sort of Petrov-Galerkin projection that we have already seen. So if we want to solve AX equals F, so we have some approximation x0. So we're indeed solving AE equal F minus x0, where is a correction. But this is expensive. Instead of solving this equation, we can solve the projected equation. We can solve the projected equation and then compute the update as prolongation of this. So that's actually almost a working scheme. So this is the way that it will work if you of course create. Now the main alchemy comes. How to construct the coarse, how to construct the restriction operator, how to construct the prolongation operator. If we are there, we just do the projection and solve. If you have many levels, we do it recursively. This is the way. So we solve on the coarse grid the correction equation. We do not do it like this. If we do it like this, we compute the approximate solution on the coarse grid, bring it to a fine grid, and use the initial approximation. It will not work. That's what I said. If you have approximation to the solution with 10 to minus 2, getting to 10 to minus 3 with an ill-conditioned matrix is as much. I will require the number of iterations which is proportional to the condition number and so on. But if you do it in the opposite way, you solve the correction equation on the coarse grid. In this way it will work fine. Explaining this in like 3 minutes without going into details is not possible. But well, the short answer is because the fine grid and the coarse grid differs only in high frequency subspace. And the low frequencies are easily resolved here, and the fine frequencies are easily resolved here just by a few iterations of the standard derivative method. But that's another story. So that's the general scheme of the engine. There are, I think, more than 100 at least different variants of how you implement it. There is a software that seems to work quite well. So probably if you just have a very large system, the algebraic multigrid is the way to go, but at least it should be tried. But again, it involves a certain heuristics of how these operators are built, and how the coarse graph is built. So, that's the summary of the second part, what we have discussed. So we have introduced 3 methods that used to be known as iterative methods for solving linear systems. Jakob, Gauss, Zeider, and Source, so they rewrite the linear system in terms of fixed point iteration. But in fact, you can write them in the matrix form as a Richardson iteration applied to a preconditioned linear system. So there is no reason to use Richardson iteration. So you can, the only way that these methods are useful and that typically actually used quite well is to use these methods as preconditioners for linear systems, for Kralov iterative methods. And they actually can be quite good. well, especially Gauss side. If you have a sparse matrix, well, this typical method is incomplete LU factorization. There are at least 3 different variants, and there are also much more, because they have like subclasses and so on. Yeah, but that's what, elude is what's implemented in SciPy. It works somehow. I wouldn't say it works brilliantly. Elu of K works very well. It's not implemented in SciPy, so you have to look it for it or write yourself if you ever need it. Elu2 is also, and you also, there is also this algebraic multigrid stuff, which is quite complicated. But again, there are classes of problems for which it gives asymptotically optimal linear convergence, for which all these methods cannot achieve, even theoretically. But the constant can be quite large because it involves quite a lot of pre-processing. You need to construct this graph coarsening, construct operators, and so on and so forth. That's the summary. And finally,